So hello guys, welcome back to day number 28. Today we gonna finish this module which is called basic gates, and also we will quickly see the multiplexer because we don't have much time. It's day number 28 and we need to finish up to KMAP as we need to finish this circuit as we done, right? And then after 30 days we will keep on continuing little slower, not every day, and we'll see sequential circuit and other things. Like we will take down all the questions of HDL bits for sure. So if you are excited, please like this video. Only after you like it, then only I'll start. Okay. So today the first problem is this one, 3-bit population count. But actually we have already done it. So in HDL bits, I have seen it here that they have few questions repeatedly they have given. So we can skip it easily. Then we'll come to this one, gates, and yeah, there is some logic, like they are just trying to see if we can have the logic, like we can implement our logics. So here what we need to do, we had a 4-bit input. Okay, so let me give any 4-bit input like this, 0 1 1 0. You have 4-bit input, and what we need to do, we need to find out the relationship between. So here we need to give the relationship between is never bit. For example, if it is 0, then what's the relationship between 0 and this one? So that's we need to find out. We need to find out three things. One is out both. So here we need to find that if the vector and just the left side vector both are 1 or not. If it is 1, then at the out both in this variable, in this output variable, for example, let's consider this fellow for this 0. So for 0, 0 is 0 and 1 is 1, but both are not 1, right? So what we'll do, we will store a 0 in our out both variable. And then for this fellow, again for 1 next bit is 0, so it will be 0, and for 0 this is again 0. So it's a 3-bit number, right? Because for 1 there is nothing in the left. Likewise, we need to find out for out any. So out any will do the same thing but in the opposite direction, that is in the right side. And also not both. It is looking for if one of them is 1 or not. So for example, for this case, one of them is 1, so we'll get a 1, and this would be result for out any, right? And always remember, this is our least significant bit and this is our most significant bit. Here also the same thing allowed. Now for this fellow, this 0 bit, again in the right side we have a 1, so it will be 1, and for here the right side is 0 but 1 is 1, so we'll get a 1 1 1, right? And for the out different, so for out different we'll learn a very small concept here, little bit, but this is important when you do pattern recognition in your finite state machine problem. So there are many times we try to detect the pattern, so there the small concept is there which will be beneficial. 1 0 1 0, yeah. For example, for this fellow, in just the left side, which one is like, are both are different or same? If it is 1 1, store 0. If it is different, then store 1. So for example, if I have 0 and 1, so we will store a 1. For this fellow, again they are different, so we'll store 1. Again for this fellow it is 1. But here what we'll do, we will go for the wrapping around. So this is a small concept which I was mentioning, and wrapping around means for this one we will just go wrap around and we'll find in the left side it is 0. But this thing we need to develop using our Verilog. To build this circuit is very simple and not truth table, nothing is required here because we already know. For first one we want to see if both are 1, so AND gate will help. For second, if one of them one or not, OR gate will help. And for the last, we are comparing if both are same or not, then XOR gate will help, because XOR gate report you 1 when anytime we have a different bits. So here what we'll use, we will use the concept of concatenations, right? Bit concatenations. So we will use this curly braces. First we will take the third bit of in, and we want to find if both are 1 or not, so we will use our bitwise AND and then int 2. And likewise we will do for other bits. So this is for your out both, and we can use the same thing for our next output also, which is out any. Just change the AND logic with our OR. And hey guys, if you haven't liked, please like the video. And for the last, we'll use the XOR. As I said, we are doing the wrapping thing. For 3 we are checking with the 0 if both are same or not. Okay. And one thing you must remember, anytime you are solving questions in HDL bits, sometimes we just carry it forward. We don't keep looking every detail, but you need to. For example, here, this out both need to be of how many bits? 2 bits, 3 bits, how many bits? It should need to be 3 bits, right? Our input is of 4 bit, but our output both is of 3 bit, or out any is of 3 bit. The reason is that because for one of the bit, neighboring bit is not available, but for the out different we are having 4 bit. And why we are having 4 bit? Because we are doing the wrapping around. And this thing you just keep reminding yourself, because soon when you start coding in outside world, outside of HDL bits, this every minute thing you need to consider, right? How many bit it need to be, and that time you can't say, hey, I need a help from HDL bits. So that's why keep on reminding yourself what is happening, how many bits are used, those things. Okay, let me submit, and we got a success. So we'll quickly go to our problem statement, and then even longer vector is the same thing, just they have increased the vector. So please do it yourself. So let us go to the next module, which is the multiplexer. So in multiplexer also 2 is to 1 we have already visited, and in multiplexer there is little differences. For example, here they are saying, I won't be doing it, we have already done it, but I'm telling you one concepts. Create 1 bit wide, right? So 1 bit wide means you have your multiplexer here, and in the output selection would be, for example, if it is 2 is to 1 multiplexer, then selection would be for sure 1 bit, because we need 0 or 1. But in the input you could have a single bit input, or you could have multi-bit input. For example, if I have a bus here of 8 bit, 8 bit, then in the input how many bits we are having? We are having a 16 bit input, like if we combine. And at the output we again will have a bus of 8 bit, because we will select one of them. But we will never call it as a 16 is to 8 multiplexer. There is no name exists like that. It is still a 2 is to 1 multiplexer, but it is a bus multiplexer, and we will call it a 8 bit wide 2 is to 1 multiplexer. So just keep this terminology in your mind, and for that only they have given a next problem, which is your 2 is to 1 bus multiplexer. And here you will see, if we go there, you will see they are saying 100 bit wide 2 is to 1 multiplexer again. For sure in the input we will have 200 bits, but we are selecting 100 at a time. The solution will be exactly same, and if you want me to quickly show you, then let me do it. So we'll say assign out equal to was the condition, and condition is selection. If selection is 0, then select A, otherwise B. So this will be true if selection is 1, so I'll select B, else I'll select A. That's the one line code, and see, we got a success. So please don't get confused. Okay, so we will just skip this 9 to 1 multiplexer. 9 to 1 multiplexer, there again we will have that concept. There is one concept is there, right? We need to assign all the output combinations, right? So here 9 is to here we are building 9 is to 1 multiplexer, but to select 9 input, from 9 input how many bits you require? 3 bit select line. Can you select 9 possible combination? No, with 3 we can go up to 8. For 9 we need to have a 4 bit select line, but if you take a 4 bit select line, the problem is that in that select line the combination we have, and those are 16 combinations, but we will provide output only for 9 combination. What about for other combinations? You need to provide something. If you don't provide, it will form a ledge. You wanted to design a combinational circuit, it become a sequential circuits, so it is a wrong thing. And that's why it's bit important to keep an eye on it, but we had already done such kind of problem previously, so I am just keeping it. You do it and you should get a success message. Okay, here they have said actually, for all other combination from 9 to 15 where we don't have an input, set all output to 1. So you need to do it. We will go to this one, 256 is to 1, and there actually we have a question from Riyaz Hassan. He have written many days ago, I'm sorry, but I'm answering it today because we'll solve that one. And he have raised a question, and we will see why it is happening actually. So we'll come back to this question a little later, but before that, what we will do, we will try to finish this one, which is the easiest one, and the next one I will go there. So here what we want to do, we want to do, actually both are easiest one, but in the second one there is some tricks are there. So yeah, Okay, so in the first problem, they are saying create a 1 bit 256 into 1 multiplexer. So it's 1 bit wide. So don't get confused that what it is saying. It is saying that we have a 256 combination of input and each input is of 1 bit only. That's the simple thing. So now to select upon 256 input, your selection line, how many bit it need to be? So it need to be 8 feet, right? And see, they have already defined it. But when you go outside of HDL bits, this thing you need to decide. For 256, how many bits is required? And one easiest way is that just convert this 256, it's a decimal number, to a binary number, and you will get how many bits you need. So we know we can generate our multiplexer using if conditions. For 2 is to 1, for 4 is to 1 multiplexer, it's okay to use the if. More than that, we will go for a case statement, but here it is a huge number, 256. So for 256 we need to write 256 lines of case statement, which is not possible. So then how to go with it? Then we have an easy solution actually. If you just think around the logic here, what they are saying, if your select line is 0, then select in 0. If your select line is 1, then select in 1. If your select line is 2, then select in 2, and blah blah blah, go forward. But one thing is very important, that is your select line, if select line is 2, then in is 2. So if I just write this in select, because if select is 2, then select 2, you getting the connection, right? Then our problem is solved. And good thing is that in Verilog, the latest 2001 Verilog version, it is supported. Your select, here select is a variable, so your index could be a variable, it's all okay. But we will have the problem when we'll go to the next problem. We will see what's the problem there. Okay, so here it would be only one line solution. You might be getting surprised, but yeah, because your out is of 1 bit, so I can write directly out equal to in and then the select and see. And that's the benefit of actually behavioral description. This circuit could have many gates, many things. So if you want to go like write the description in the gate level, it will take at least your half an hour to 45 minutes. But with behavioral domain, we can write in one line and we can just try it out if it is working or not. If it is working, then we have the facility inside the Verilog tools, the commercial tools, where it can generate from here to the netlist or to the gate level Verilog code. And then we have RTL JDS, which can directly go for the layout. So that's why things are getting very automated, and that's why we have the VLSI, right? That's why we can design a chip out of billions of transistors. Okay, so let me submit and see if we are in a correct path or not. So don't get afraid that hey, everything is automated, then what's the use of VLSI engineer? Things are getting automated, that's why VLSI industry is there. Otherwise, we can't have a VLSI industry. Humanly it's impossible to design so many gates inside a 1 year, right? Because every year we are having new chip. Apple M1, M2, Intel 14, 15 gen is coming this 14 gen, I guess, in December. So that's why VLSI is existing. So don't get worried about those automation. Hey, it's gonna take your job. No. Okay. So it's we got a success. Now we will go to our next problem, and here we will face a problem. But before facing a problem, we will try to solve it. Okay, so here the same thing, but it's a 4-bit wide. So if it is a 4-bit wide, then the problem we are facing, and that is in the input you don't have 256, but you have 256 into 4, which is 1024 bits, right? So now what is happening here? See, when your select line is 0, previously when our select line is 0, we were directly selecting in 0, but now you can't select in 0, right? Our input need to be a 4-bit wide, so we are selecting actually in from 0 to 3 bit, like 4 bit. When your select line is 1, then we are selecting in 7 and 4. So that's that same logic which we used in your earlier problem is not working here, right? Because for 1 bit is very easy, but now it's 4 bit. Okay, so here we need to see if we can use some logic by which using select line only we can propagate our index value, and we will actually have a solution, and that is we can write it like that: into 4 plus 3 and then select into 4. See, these things are not coming in 1 second. You need to think of the logic, you need to use your trial and error method, and then only you will find out this expression. So don't worry that, hey, how I am getting it. I have solved it previously, that's why I know it. If you are or if I get some new problem, then I need to think sometime 10 minutes, 15 minutes, using different combination which is working here. We will try if it is working or not. So don't worry, please don't get worried. Okay, so when your select is 0, you are into, so it will be 0. Your selector is 0, so here we will get 0, you will get 3. Okay, when selector is 1, then here select into 1, we are getting a 4. Perfect. Here select into 1, 4 plus 3, 7. And the same thing will work for this also, because in a 7 it will be 2. So 4 into 2 we will get 8. And for 11 it will be 8 plus 3, 11. So it's simple, right? Actually, it's really simple. You just need to first go for your first index, fix it, and then just plus the 3, because you are propagating by 3 bits, right? 4-bit wide. If it is of 8-bit wide, then we would use a plus 8 here. So don't worry. Okay. So we use this one, and we will try to use it here. But if we use it like in this question, what he has mentioning, he has tried this one. See this logic here, but this logic will give you one error, which should not be, but it will give you one error. So I have written about this logic which we have find. We are submitting it, and see we got a error, and in the error it is saying, hey, your cell or the select variable is not a constant file. So now what is happening here? See, this problem is happening because the compiler, the synthesize, yeah, compiler is not perfect here. That's why we are having a issue here. It know that your out is of 4-bit, right? But you are giving a vector or a vector select here, one part of in you are selecting here, right? And here it is unable to detect what's the size of select here, like what's the value of select, because it's a variable here. In the previous case it was working because it was only 1 bit, so that's why it's unable to decide the value of select and what would be the expression, because here we are doing some mathematical expression, right? And which is not supported, unluckily actually. So we need to go with a different approach, and it's the same thing they have mentioned here in the hint section in the HDL bits. Your vector indices, the things we are writing inside, these are your indices, can be variable as long as synthesizer can figure out what's the weight of those bits. The problem is that it's not always good at this. So, and it will say you error, and which error we are getting. I also don't know exactly why this is happening, but I will, for now I'll just consider that, hey, it's a limitation of our synthesizer. So then we have the alternative. So we'll try the alternative, and alternative is using the, like, using each vector, each bits. Here what we are doing, here we are just giving a range. But what we, if we do that, hey, we will give it each bit of the out, because your out is a 4-bit, right? So we can use our concatenation and defining each bits here 4 bits, then our synthesizer won't get confused. So I have copied it 4 times, and then we will just do 1 plus 1, and then plus 1, 2 actually, and then plus. So just mind that previous solution was logically exactly correct, but it was not our fault. We are getting it wrong. It's the fault of the synthesizer. So don't get worried why it is not happening. It's theoretically it is perfect. But just to help our synthesizer to understand what we are doing, we are using the concatenation alternative here, and we are defining each bits of our out, right? The similarly we have did it, right? 1 2 problem before, so same thing we are trying here. And let's submit and see if now it can give us a success. And in meantime, I am seeking for your feedback for all those 28 days, 38 days, how I have performed. In the below description we have the link, please go there. Many of you have given already your insights, and those are very insightful. I am thankful to you. I got 19 feedbacks, and 19 number may be small, but 19 people have taken their 2 3 minutes of time for me, so it's a wonderful thing. Yeah, I will get a success. So if you haven't done it, please, after this video, please go to description and give me the feedback. I need it. Okay. So our multiplexer is done. Now we can start with our arithmetic circuits. And arithmetic circuit also see half adder, full adder. We have already done 3-bit binary adder. We have already done. Actually, we have done this one also. See, 100 bits binary adder. We have done it. So wonderful things, right? The only important thing which is left in this one, 4-digit BCD adder, I think we have not done, but I have given you for a homework, so we will try if we want to solve it. But yeah, this sign addition overflow is important because in number system, anytime you go for a digital electronics interview, they will ask for number system, right? So we need to get a more of number system. So I will suggest you today, you please revise your number system, like one complement, two complements, and tomorrow we will try to solve this one. Here they are using two's complement theory here. So please revise your two complement, and we'll see you with this problem, 4-bit digital and KMAP also, and many other problem. Till then, keep smiling, visit the description, give me feedback, and tata, bye bye.